Hello, let's talk a little bit about 3D objects and how to read them. So here we got a wonderful box. It's a box in FBX format. FBX format is AutoCAD, I think. It's used a lot in Unity, so that's why it's kind of nice to be able to read them. I have a reader here and it's horrible. I mean, it works and that's the basis of it. It's not beautiful code. It has a lot of bugs. But it's basic that works, which I will rework to a loader that actually is the real loader, more or less. It does not support animation at all. So far, I haven't looked into animations yet. I need just to take some time to refactor this code into something that's actually usable. I'm thinking if I should release this code or if I shouldn't release this code, because this code could probably be more trouble for you than actually worth. But we will look into how to read objects files anyhow, and a format that I think is a lot simpler for you to read. I do not have a code example for it. Well, technically I do, because I have written a loader for it before, but it's not in this project. Anyhow, might release it later, might not. It has a copyright on it. Anyhow, let's look at this box. So the box is an FBX file. And an FBX file is a Unity file, and we will ignore what's on the screen right now and go to the asset store over here. And this is the Unity asset store. In here you can find all sorts of art if you are not good at art yourself. They cost a bit. This one costed a lot. So don't download this one, but it's the asset pack and you can get cheaper ones than this. I just got something on my phone. Nothing important. And you have a lot of 3D for your Unity project, but of course we're not using Unity, because if you were, you wouldn't be looking at this video. So we're going to load it in code. And what you're going to do when you're going to load an object in code is you're going to get this library. It's called asset import lib. It's from Germans and they thought it was fun to call it asimp. I'm not sure that's as fun to Google for, but yeah, it's at asimp read the docs.io. I don't know. That's probably just the documentation. This asimp.org, and then click on documentation. And you get here, and then you have introduction, and here you have all the formats that this library can read. So go there, grab that library, start reading your files, or you be a stubborn asshole like me and try to read them yourself, because you learn a lot. You don't need the dependencies. If they update something or doesn't update it or delete the asimp library, or you don't have it on the PlayStation Portable, or for whatever reason, if you have your own loader, you don't need to care about any of that, and you have all the copyrights on the code, which is fine. So we're going to look at three different format types. We're going to look at the old school wavefront.object file, which is super simple to parse, and you will be able to write a parser for this without the problem. And then we have the 3DS, which was kind of used a lot back in the day. It's more for simpler styles of 3D models. It's not true. It's not for simpler style really, but back in the day, the objects was of simpler style. And then we have the FBX, which I would say is a modern format. 3DS seems a bit harder to find these days, but you can always export it. Import it in Blender. You need to enable a plugin. For export it to 3DS, you can export it to 3DS. We will look at those three, because I think they represent a very easy format to read. A format that gets you into binary formats and how to read those without being too difficult. And the FBX, which I do not recommend looking at all. Get the asimport library, or get my loader when that one is done and working. So let's start with explaining what's inside one of those files. We're going to have vertices. And vertices are just points. And the vertex can have a few attributes. I can have a normal, go to draw a normal on all of these. Now that's a normal is the vector. So the vertex, the point, of course, has x, y, and z. The normal also has x, y, and z. And it's just a vector, meaning a direction. So it just points some direction. You don't really care about the size of this vector. This vector could actually be just described with two values. It could be described with two rotations. That would be enough. Have a rotation around x and y would be enough. But x, y, and z is normally how they are described. And then the file will contain something called a face. And the face will be a polygon, of course. The polygon can have 4 vertices as corners, or it could have multiple. So it could be a quad or even bigger, so meaning 4 vertices. Could be so it'd be just a square rectangle. And then we have a UV. Let's see, we have green here. So we have UV coordinates also. So each vertex here will have a UV associated with it, and some might have multiple UVs associated with it. So here we got the vertex with multiple UV. And the UV is the XY in a image, in a texture. So I'm going to texture this corner here. I'm going to interpolate between this UV down here and that one up there. So I get where in my texture I need to pick the color that go into the polygon. So all of this is contained within those files. So we have, let's go through it again. We have vertex data, which doesn't have to, but most of the files have an array of the vertex data, so it just comes in x, y, z, x, y, z, continue, 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 and it continues until we covered all vertices. Then we have normals, which is the same. It's just x, y, z, same. And that's these normals. And normals are used for light calculations. So when you have an array of light coming down to the surface, hit the surface, the normal is 90 degrees. It's going to go out at the angle it came in. If it's not, it's going to bounce another way, right? So those can be used to calculate, what should you call it, local shadows? Calculate how much light will be hitting the camera, you in this case, from that specific point. And then we have, that wasn't very nicely drawn. Then we have the face data, which normally is represented in a total different way than the other two that we had. I think we get back to the face data. Let's do the texture data before that. So we have the texture data. That's just UV, UV, and so on. So that's like stored the same way as the vertex data, stored the same as the normals data. The texture data, the UVs, are, instead of the others being 3 values, x, y, and z, this one going to just be 2 values, UV, 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 repeated. But the polygons, they are most often stored in something called just index. And they indexing the other values. So they are, it could be, let's say 3, 2, let's calculate backwards here. There we go. So they're just going to have numbers like 3, 2, 1, 0, which means the first vertex of this polygon. First we need to know how many points this polygon has, like vertex. How many vertices does this polygon contain? Normally 3, right? So it would be 3 of them. We need 3 values. We got 3, 2, and 1. The first one, number 3, reference offset number 3 in the array up here. So it has x, y, and z. Those are offset 0. And then we have offset 1, offset 2, and offset 3, which I haven't really drawn in here. So that's the x, y, and z value we need for the first point in this polygon. Let's say that that's the point up there. And after that we need 2, and that's 0, 1, 2. So that's this one with an x, y, and z value. And that would be this one if the polygon is clockwise. And after that we have 1, and that's this one, and that's the values down here. So now we have all our corners for our polygon. So we have our first polygon, but then we need the normals to calculate the lighting, and those works exactly the same. It's the same 3, 2, 1, just in a different area here. So first that one, then we have this one, and next that one. And that's the values we need to draw out our normals. You can have 2 different index arrays here. You could have one for faces, one for normals, and I mean in extreme case you can have one for UVs also, I guess. The UV is going to work exactly the same. So 3, 2, 1, and we need the third. The third was over here, but this time we just got UV, not x, y, and z. So we just got 2 values instead of 3. So that one is for the first up here. Then we have the second one. Now I offset it wrong with 1 here. Is the next one, and the last one would be here, and we have the number 0 out here because I offsetted it wrong here. We started with 3, which should be the one here, but yeah, I offset it wrong. Anyhow, messy description, but this is the data we need from this from this graphical format, right? Let's see if I can clear up my screen. We can actually go into the code and look at that. My code is messy. This is test code. Hard coded the size, max size. Let's ignore all of that. You haven't seen that. Let's see where they uses these vertices. Apparently a lot of places. Where is the draw? Calculate. Oh, here. Here we go. So here we, I said no code, but no code in looking at the object formats, the 3D models. But okay, a little bit code of how to render it. So we're going to enable client state vertex array. We have an array of vertices with what we have loaded up from our file. We have an array of texture coordinates, the UVs that we loaded up for the file, and we got the normals for lighting that we loaded up for file. And then we're going to do GL vertex pointer. We have 3 points on this, so this vertex pointer contains 3 values, and then it's something we can skip over, which is 0 in this case, and then it comes 3 again, skipping over 3 again. And those are floats in my case. They compact, so they are like stacked together. There's nothing in between them. That's called stride. So a stride of 0. And just pointed to the vertices. Then we have the texture coordinates. Same thing, only there's just 2 of them. And that's a float, and we have our texture coordinates, a normal pointer, and that's a float, and a normal pointer only can be in groups of values of 3 all the time. So this vertex pointer is that pointer there. Ignore that. I was thinking being smart, I'm not that smart. So let's see how, so we set up this first, and this will send down that data to the graphics card more or less. And then we go into our display function and we're going to render it. So here we've got the render function. Draw elements. We want to draw triangles. Triangles are the word for polygons. We're going to draw that many polygons. We have them in GL unsigned int in my case, and that we're going to draw the indexes. So we go to the index array, looking for the number there, and from that number we have index into the vertex array, into the texture array, into the normals array, into the texture array, just different size of records in there. So this is the call for drawing everything. So let's do that. Well, that's that. That's what you have seen before. That's my test object. But let's look at another object and then go to, just for fun here, just load in another object. That was the texture that I hard coded in. I have a image loader also, by the way. Might be coming up in a later video, but now I'm just including it like a C file because it's so super simple when I'm testing stuff. So this is just another other object, and that's actually the object we're going to look at in the file now. So let's jump over to see how one of those files actually look like. So here we got cat object and untitled object. I don't know what untitled contains. So let's look at the cat object. And this is the wave file format, which I think wave front, is that from Lightwave? I think it is. Lightwave. Wavefront. Wavefront object. Wavefront object. Wikipedia is very good to explain files if you do not know how they work, right? So start there. Let's see, Wavefront Technologies. Did they do Lightwave? I'm not going to look at this page right now. I'm not totally sure. Anyhow, too much jumping back and forward. Now the file for, I think the third time, right? So you should start with Lightfront object formats because they're easy to parse. They are text files. And we have gone through what they should contain. And here you see that they will contain that. So first we have a header. I save this in Blender because I transformed this, I exported it. I just got a notification that says ignore me, it says. So I have a Blender, I exported this. The first line here it says material lib. So this is another file. You can look at that one, the cat mtl. This explains what textures this file is using, and we're going to ignore this file totally. Just ignore it. We don't need it. The first here says O, which is object, and we have mesh 0. That's our first object. Our first mesh is described down here. Mesh is just another name for an object. For 3D object, a mesh. I guess it's the mesh of points. I don't know. But we got V here for vertex, and then 3 values. A V, another 3 values, another vertex, 3 values, another vertex, and it just continues like that. So you just open this file, write the file loader, that's just go through these lines until it gets to the end of those VTs, which I happen to know. Oops, I happen to know it and say and I get wrong. VM. There we go. So you just read line after line after line after line and store them in an array, and then also calculate how many lines you have read. Good idea. And you get to the end, and after that you get to the VN, which is vertex normals. So that's for the light calculations. So here you got the normals of the object, and you're just going to read line after line after line after line after line and count how many you got, and hopefully you got the same amount of vertices and vertex normals, because you need one normal per vertex, so you should have the same amount of them. And let's see where it ends here. So you read and calculate until you get to the end. And when you get to the end, you will end up with VT, is this vertex texture coordinate, and those are just two values. And as you have guessed, there's as many of these lines as there is of the vertices and the normals. And I actually do not know what the name of the next lines after this are, so we're just going to scroll for a while. There are a lot of vertices in this cat file here. I will check in this cat file because I own it, so I have the copyright to do so. From what I know, at least, I'm going to check in that at least, so you have an example file to look at when you start coding your stuff. And it was good that I scrolled down, because it wasn't what I thought it would be in the end here. It has an S1. I know what the S1 is, or I knew what the S1 was or is when I wrote my loader. I have no clue what it is right now. I think I at the start just skipped over it. Yeah, that's skip over it. And then it says it's going to use the material 0. The material 0 is in this other file. New material 0, NS, NK, KS, and KE. Who knows what that is? Ambient light, I would guess. Specular light, maybe. E, I have no idea. And then the file. So, yeah, not gonna use. So let's go to, was it face? It was face. So polygon is also called face, right? So it would be very common in the files that we're looking for polygon data, but it is named face data. So we have the face, and this is the polygon, and the polygon has 3 vertices, and this is a group of 3 values, which is the vertex, normals, and texture indexes in those other arrays. So we had the vertex arrays, vertexes, we had the texture coordinates, and the normals. And that's just the vertex. I'm not sure if this is texture or normal. If you get wrong, you will notice, and you switch them around and you get the correct one, because you will see the object from just the vertex, and that's the first one. And if the texture is wrong, then you got one of these wrongs. So, and texture, and that's just index into this somewhere. And lucky enough for us here, it's 111. So it's actually it's just the first value. That's all of that means. And we have the first group here. That's our first vertex. Should probably have drawn that in yellow. Second one is our second vertex. Third one is our third vertex. And then we can draw our polygon. And we have our normal data, so when we get light in here, the graphics card knows how much light to put on these pixels here. And then we have the texture, so the UV for the different corners, so it can calculate what part of the texture is the texture in there. And we do that for all these faces. And let's scroll through them. There are 21,000 faces or something like that. And this object is way too many. Don't use that object for more than Did I show the cat, by the way? I think I did, right? Yeah, I did show the cat. I had the box from the start, I know. So now we're up in 20, I see the index 21,000 here, so we are soon at the end of all these polygons. No, we're not, okay. Because in the start here, it was really like small numbers getting higher and higher, but after that it gets really random here. So it can be extremely random. It started at 111, now it's all the numbers seems to be more or less random. So it's jumping through this array. And why it's doing that is to save memory. Which I actually have the question if it really do save memory, because this face polygon index array also takes memory. So I'm not so sure it actually saves memory, but I guess it does. I mean, else we wouldn't have it. And it's extremely common also, so. Oh, the file just ends at the end. So if you would lose something of this file here, there's no checksum of that. So that's basically the wavefront object that's easy to read. And how do we get this kind of information? We just Google it and we got wavefront file format. This is a comment. Okay, so comment looks like that. List of geometric vertices in X, Y, and W is optional by default. So you got vertices, list of texture coordinates. Okay, VT, coordinates, apparently it has the W also, that's default. Normals, parameter space vertices, I have no idea what that is. Polygon face, line elements I haven't found yet, so. Yeah, and description of it. Easy peasy. If you do not have wavefront objects, which is easy to read, you can start Blender. Just delete this. Go to File, Import. Let's download something from. Wait, should we actually do that? Nah, not now. I'm lazy. We're just going to import a file, FBX file in this case, a Unity file. So you go to the Unity store, you select something, you download it, and here you got your cat. How do I zoom? Am I stupid? There we go. We got cat in FBX format, and we're going to export. Oh yeah, it's best to, at least when you start, to only have one object. Unity files, FBX files mostly contains multiple meshes per file. It's great to just have one when you're starting out to create writing your loaders, as actually easier later to only have one per file anyhow. So over here you got a list, and if you have multiple meshes here, you might want to delete them until you just have the object you want. And then you go to File, Export, and we should have wavefront object here. So we can export this. I won't do this because I already okay. I will export to that. Now I exported the cat as wavefront, even though I downloaded it from Unity Store. So now we have it in the text format, and we can write a loader for it. But let's jump to the next file that's also easy. So that's the text format, and I think you should start when you're writing loaders there, if you don't go for the asset import library, of course. But if you want to write your own loaders, then start at that file. And when you want to look at binary files, let's see if I have one of those. Do I have a 3DS here? Ah, see, I was smart. I exported the cat as a 3DS before. So when you want to look, start at loading binary files, then start to look at this file format, and it will look like crap. So now you're down into the matrix. So you need a tool to look at it in a non-textual way. So you can't load it up in Word or something like that because it has unprintable characters. So you need something like command less to look at it, or object dump. And I'm using this terminal is called msys. You see here msys there. So you could download msys, and that comes with this. So you need a type, and I want is it x1a? Is that the type I want? I think that's hexadecimal 1 byte. Hexadecimal 1 byte per value, and I want to dump it in ASCII also. And I'm going to pipe it to less, because else it just scrolls by. So here we have the binary file, the matrix shit, and it has a magic MMD apparently, and then it comes just a lot of things. Let's go through a very common binary file format, TLV. Many binary files follow this format. So you know this format, and you have an object dump utility, hex editor or something, Google hex editor, download one, and you know TLV. You can more or less, I was going to say decode most binary files, that's wrong, but decode with some difficulty and Googling your binary files. So TLV stands for type, length, and value. And I will draw it like this. So first comes the type, then comes the length, and then comes some value of some sort that has the size of the length in some regards. So if you have a file, and the file can contain, this is called a record by the way. A file can contain multiple records or just one record. So this could be represented just one file. So if you have a file that's 2000 in size, and we got a TLV value in it, so it starts with something, let's say this starts with the two letters MM. And in this yellow part, the length part, that should describe the value, length of the value, that has to be close to the 2000, because we know the file is 2000. So maybe it's 2000 minus these 2 bytes, and this is normally like 4 bytes or 8 or something like that, so minus 2 minus 6 in this case. So it has written down in 1994 as value in that length value, and then comes some value, and these values can have two different forms. It can be the value we're going to read, so it could be the vertices, often an array of them. It could be another record also, so it could contain another record in here. That's called a child record, and that one was also going to include a type, where's yellow, a length, and what color do I have? Green for a value. So here we have a file that's 2000 in size. It starts with a magic. That's the MM. After that comes a length. And this is a little bit after that. It also comes a length. It doesn't have two. Normally files could start with a header. So you need to like Google a bit as a file header. Say, does this file contain a header? And in this case, after that header is done, is it chunked data? Chunked the data is also a name for records like this that has records in it. Is it chunked data or not? Does it follow the TLV? And after length, it has a value of some sort that could be just a value that we need, or it could be another record. So you have child records. And the file could be that it's not just containing one record, it could be containing multiple records. So maybe it comes another record directly after, another one directly after. And if you have some streaming format, so you don't have a specific file size, it just comes streaming over the network, then this is extremely common. If you have a video stream sent to you, this could be just the first one, can you see that? Yeah. So this could be the first frame of it, and the second frame in your video, and the third frame in your video. Easy. I mean, it's not that easy, but kind of. So you're going to Google like 3DS file specification, and I ended up at Wikipedia on all of this, so let's start there. So structure, 3DS is a binary format. The format is based on chunks, already mentioned chunks, where each section of data is embedded in a block that contains a chunk identifier. Chunk identifier is the type in the TLV, and the length, that's the length in the TLV, of course, and the data, that's the values in the TLV, to provide the location of the next block as well as the data itself. So again, we have type, length, value. Length will point to more or less the next type, length, value. Length will point to the next type, length, value. Okay, that's why I should point to the type there. Length will point to the next. Yeah, you get the point. And the reason why binary files, not all of course, but some of them is done like this, and it's very common, is because you can introduce types later in a later date. So you could support a type. I support the type 1, I support the type 2, and I support the type 4 over here. But for some reason, when I'm reading this, I'm reading a newer file from a newer specification, and my loader don't know about, because type X comes here. I don't know, type 128 or something like that. Something I do not know. Even though I read the first one, I know what the first one is. Where's the green? I read the first one, works fine. I read the second one, fine. I know what that is. I come to the third one. I don't know this one. I haven't seen this one before. So I can't load this file? Yeah, I can. I still can. And that's the strength of the TLV. Because I'm just going to read the next and like, oh, I know the length. I know how much I should skip. I know how to skip over this value. I don't need to interpret it. I don't need to read it. I just skipping over it. And I get to the next type, which I hopefully know what it is. Length value. And it continues. So the chunks form a hierarchical structure. So that means we have a record. We have record, TL, and a value. And the value is a record. It has a type, length, and some value. So it has those child records in it. So the chunks form a hierarchical structure, similar to an XML DOM. They have to write out that so people from this side of the century know what that is, I guess. The first 2 bytes of the chunk are an ID. So the first 2 bytes are our type in the TLV. From that value, the parser can identify the chunk and decide whether it will parse it or skip it. So you can skip it if you don't know what it is. You see where I'm getting at this? The next 4 bytes contain a little endian integer that is the length of the chunk. Okay, so that's the length. So we have the T with the ID. Where we did there we have the type. We have the length. So the next 4 bytes contain a little endian integer that is the length of the chunk, including its data. The length of the sub blocks and the 6-byte header. Okay, so we have a 6-byte header. So let's again. So we have the type, 2 bytes, 1, 2. type. At 1, 2, 3, 4. It said here 4 byte. So we got the length 4 byte, and then we got the value, and that value including its data. The next 4 bytes contain a little ending integer that is the length of the chunk including its data. So I would say that that's including its data. The length is of its sub blocks and the 6 byte header. I would say, I'm not totally sure, that the length specifies this whole thing. That could be different from different files. What the length, do the length include this part or just this part? Below is a list of common chunks. Okay, so it's going to start with the main chunk. That's 0, 4D, 4D. Let's see if we can find that. So we have this, we have 4D. Oh, okay, was the first bytes of this file. Do we have more 4Ds? We have one, but not 2. Okay, so that's our type. We found our type, and then this should be the size of the file, and then we need to figure out how to read this. And I don't know the size of the file now, but I would guess 001244 is the way to read it. So let's go to Google and say hex to dec, because I need a hexadecimal to decimal converter. And then we're just going to type in 001244 convert, and we get the file size that like a megabyte. That's kind of big. I wonder if this file really is that big. Let's find out. And look at that. That's exactly the same, right? That's exactly the same number. 1197, 134. Yeah, that's exactly the same. Which means that we have found that this format has a type, a length, and then damn it, if the rest here isn't the value, it has to be the value. And now we can see this says 0002 here. So that should be, wow, I need to learn those key combinations. Let's see, where was the... So I had 0002, 002, M3D version. Okay, so it's a version. It comes a version after that. Then we have another record after that. That should be 3D. So let's bring up the terminal again here. Do we have 3D? There we go. So then we have, let's get the size here. I have to look at my other screen here. So we got this version here, the type, and we have the size here, and 0000000A is 10, so it should be 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's our record. And our next record starts over here with 3D. I'm sorry for drawing over the old there. That's what you have seen my videos before. They are being messy. So it starts with 001244 3E. Let's go to decimal converter. We have 0012 1244.3e convert, and that's almost the full file. So I would say that this record that comes here, the value of it is all of the rest of the file here. And we can of course check that if we want to, because we know the size of the file, we know the record size here, take one minus the other, and it should be these, and that happens to be 16. So let's see if we have decoded this file. And we go, let's check, we have the size over there, let's check the size here. It's 1196.118, and this is 134. Is it 16 between there? And I think it is. So we have decoded that we have a file in TLV format. We managed to decode the first record of it. We decoded the second record of it. We skipped over the value because we didn't care about it. We got into the value we did care about. And check the specification here. We are at the 3D editor chunk, and all the rest works exactly the same. So now you can write an importer for a binary file in 3DS format. So you have object block, triangle mesh. So triangle mesh. So we need to read this 4D 4D. We need to skip over till we find 3D 3D. We need to skip over till we get to 4000. We need to skip over till we get to 4100, and then we have triangle mesh, and let's read the triangle mesh data. So when we get to 4110, then we got vertex list, and you recognize the vertex list. 4112, faces description, faces, could that be the polygons? Could be, right? Faces material we can skip over, smoothing group we can skip over. Mapping coordinates list we can skip over, local coordinates system we can skip over. Oh, it apparently contains light, we can skip over that. So we need normals here. So we got faces, we got vertexes and faces description. I guess the faces description are polygons. I would guess that. Could actually go in and check in my loader, but so the file could contain light data, camera data, material block, which we could totally skip over. Do we have a normals here? We could skip over normals also, but do we have them? Normal. Accurate vertex normal cannot be stored in 3DS files. Instead, smoothing groups are used. Okay, so we cannot store vertex normals in 3DS. Okay, sure, cool. Let me know that. So we have vertexes and faces. Okay, well, let's skip to the next file. And I don't have an example for you for this, but what I do have is another file here. So let's jump into that one. We have the dragon wolf polygons here. I did show a cat before, so let's jump into this dragon wolf. It's a dragon wolf that I created with lighting, and it's loading the FBX file, so Unity file this time, and it's a really hack, but maybe I upload it. If it's uploaded, check the description for the code. And we're going to do exactly the same. We're going to Google this. Let me check over here first. Oh wow, I recorded an hour. Sorry for you guys following along. Those two of you that following along. Cheers to you. So we're just going to Google FBX file specification and then find the best link we can get. And the best link I could get for this file format, let's see so we can see full. There we go. Was from Blender and someone guy that wrote an importer, or is it like an exporter? FBX is a popular 3D file format that's originally developed by Kaidara for motion builder acquired by Autodesk. It has now become one of the main 3D exchange formats that's used mainly for 3D tools. Even though Autodesk publishes its free SDK for FBX, its license and the software itself remains Fully closed FBX has the text file format ASCII and a binary version. There's no public documentation available for a binary FBX format. Yep. Blender Foundation asked someone to write this up. That has okay. So we got the text-based format. That's not the format Blender exports out to, so that's not the format I want to read. So I'm going to skip over that. Binary file structure. Here we go. The first 27 bytes should contain a header. Byte 0 to 21, so 21st first. Kaidara FBX binary space and a 0. File magic with 2 spaces and the end and null terminator. Bytes 21 to 22. Those bytes unknown but observed in all files. Bytes 23 to 26 unsigned integer versus number. 7300 for version 7.0. Let's find an FBX file. There we go. Yes, it's a muscular lava cat. And now we go into matrix shit again. And what do we have? Don't we have Kaidara, FBX, binary, and the 0, space, and the 0. So we got an FBX file. Got 2 bytes that should always be a specific 2 bytes. And then we had 2 bytes, was it? Or was it 4? Was it 2 or 4 bytes? Was it 2 or 4 bytes? It was 4. There we go. That should be the version, and we know they should end at 00. These are zeros, so it does end at 00. Question was E8 and something there, what that is. We need to go into the object dump to look at that. But before we do that, let's check this file out. Sorry, I need a coffee. So you can see that in using a less here, that's like more but less. Just another command for more. Displaying the file raw. I can read. I have actually text embedded in the binary here. So let's see if we can find vertex data here somewhere. Cast shadows, booleans, colors, vector, visibilities. I need some vertexes. Look at that. Look at that. We have vertexes. And I would guess that this is the length of the coming data here. Because I would guess that this is T, this is L, and all this rest is V. So I'm guessing that the FBX is a TLV format. It's hard to know if I am in the drawing tool, if I'm not in the drawing tool, and that's why it's so hard to enable the drawing tool and disable the drawing tool. So we got vertexes. Let's see what the next text we can read. Is it something we can read in here? Here comes something we can read. Nope, nothing I really can read. Let's continue. Has to be more stuff I can physically read in this file. You get problem if the text file is compressed in some way. Then it breaks down this how to decode binary files like this. But I need to something. Is it really nothing I can read after that? Is all this vertexes? Has to be more thing I can read. Has to be. I know it is, because I read this. I already encoded it. But let's just dump down here. Don't we have any normals? Normal. Where do we have normal? The search did find normals. Layer element versions, mapping informations. Do you have normals here somewhere? Where do we have normals? Oh yeah. That was hard to see. It says normal here. There we go. Then I'm guessing this is the size, and the rest of this crap is the value. So we found our T, we found our L. Let's get out of the drawing tool again. So we can say this much so far. This is a binary file. It has text in it that we can read. It for sure have vertex data and normals because we found them. It for sure has some way to know how many they are, so they have a length in some way. Oh, look, it actually says on this file here. So node record format. First we have a binary file structure and the header. So first comes a header, but after that it comes records. And we already talked about TLV records. So let's see if this is similar. It's not exactly similar, so it's not as easy to read as the 3DS version, but it's still there, right? So we got 4 bytes. That says end offset. So that's our offset to the end of the record. And it comes a new record down here, I happen to know. And this case is not the length, it's actually the offset in the file. So the next one going to point to the next offset in the file and the next offset in the file. So the location in the file. It's not the length of the record, it's the location, next location, next location until the end of the file. And then we have apparently number properties, which is, I will get to that. And then we have property length, that's the value length. Then we got the name, size of a name, and then we got the name, and then we got the properties. And oh crap, we have a nested record, so we can have records in records. And now I draw over it, but it said 13 null records, so every record ends with 13 bytes, that's nulls. So we know that they're going to end with nulls. And the next one also going to have 13 bytes of nulls in the end. And the next one is going to have 13 bytes of nulls in the end. So we have an offset to the next record, and that's used for the same thing as the TLV format. If you don't know the type, you can just jump that record, so you can support a newer file than your reader are. This is exactly the same. It's just, instead of saying the size of the record is, it just says the next record starts here, and the next record after that starts over there. So the format in FBX files is that they have a number of properties, and after that comes another record. So more or less like this. It actually has a name crunched in between here also, so it has a name here. And that's going to be vertex or normal. Or polygon. Yep. So it contains a name, and that's the size, the name size of that field. And we have a number of properties that could be like rotation, could be matrix, it could be a color, it could be a property telling us the format of things that comes in the next record. It could be the actual data of the vertices. So the property here could be the data of the stuff. So this is data. And then we have the next record. Okay, really messy. So that's our record format. Let me go down. probably should read this. Property record formats. Okay, so we have for each property, they also are records. And they have a 1 byte, that's the type code. And here we got the type codes. So if we have a byte that says W, that's not a W. Anyhow, a 2 byte signed integer is a Y, is a 2 byte signed integer. If it's C, it's a bit boolean. If an I, it's a 4 byte signed integer. I happen to see, we go to vertex here. Vertex. Where do you have vertex? Where is my little vertex? My vertex starts. Vertexes here. There we got vertexes. And this is D directly after. Vertex is D. I noticed that before because this says geometry L. This over here says integer S. This says enum S. So that one and that one is the type. This is the type of the record that comes. So it's the geometry record, but that's the type of encoding we have. Oh, I just noticed for no reason, geometry here, there's nothing I have coded up in my loader, but it actually states mesh here. That's the name of the mesh. I happen to recognize that's the name of the mesh in Blender. So let's jump over to text again. So we had the D in vertex, we said vertex and D. So we have a D and it says array of 8 bytes, double precision I don't know, IEEE 754 numbers. I think that's just the double. I think that's an Intel double, so we can read this as doubles. And it happens to be that, cause just jump over here. So we know now that the D here stands for we have a lot of doubles. So our crap data that comes all here, that's matrix crap here, that going to be in the format EEE7, what was the format? 754, which I think is just normal doubles. So this is just a list of doubles. Do we have any more information about it? For arrays types, data is more complex. Okay, and that's an array because D was an array. Then I have another record type here. So it starts with a 4 byte length, array length, encoding, compressed length, and contents. So we have our length again. So we have sorry for the mess here. We got our type. We got our length. Recognize the TLV, right? And we got our value. But then we have something called encoding, which I hope it ain't encoded, because then we got a problem reading it. But since we have something they called compressed data, it might be compressed. Let's read more. If the encoding is 0, the contents of the array length times the contents is just array length times the array data type. If the encoding is 1, the content is deflate zip compressed buffer of length compressed bytes. And I happen to know that it is because I encoded up this and it was zip files. I needed to use the libz to uncompress it. I do have my own uncompression code that I written because I'm like that. But I didn't use it because I wasn't sure my compression would work with this, because I have 2 different kind of compression in the C library. Kind of the deflate library has 2 different. That's another story. I'm not sure my code will work. I use the library. And let's see if we have something more. Both of this is for, okay. So we have, let's go over it slowly again. We have a header. Oops, we got a header. We got a TLV node record format that's hierarchically, that can be child nodes inside each other. I know that because it says nested list here, so it's nested records. Each record has a name that has a number of properties, so it could be colors and RGB for colors. We have another nested record. The proper record, the property has a type, The type could be primitive types. That's easy to read up. Those primitive types is easy. Could be an array type. And we know that vertexes has a D as an array type. It says here how to read it up. We know that an array has this record format with the size and compression. And then we also have strings and raw data. So if you have the name of the mesh somewhere, which we do have in here, if I search for it, that would be a string. And that has the format of a record that looks like this. So it has an S and, oh, we actually had an S here. We had a lot of S's here. Here, interlace mode, S. So this should be a string, but I can encode this and see that this says 000. That's 000 and a D. And the D is, what's the D in hexadecimal? F is 15, right? So E is 14, so D is 13. So we've got 13 bytes after here then. This says enum as. Yeah, a little bit unsure about that one, but you get the point, I think. So I said not talking about code, and we shouldn't, because I won't really go through it, but we can go through it and see that I actually followed this. So I took and wrote in, let's see, I wrote in header, calculate the header size. We have a node record. It has the end offset, num properties, length properties, nested records. That's the size of the header of a record. Then I have some functions to reading integers and shorts and floats and the formats that was specified. So we got a function for verifying the header that is the correct file. So I just checked that I have enough size to read the header. I checked that it starts with a magic in the file. There was 2 bytes that was always the same. I checked that those are the same that I expect. I checked the version. I only support these 2 versions because that's the only 2 versions I've got an FBX file for. For anything else, this loader won't load anything. Then I have some read 1 byte. These aren't used. I haven't found any data that really uses it, I think. Then we have the read an array and double precision. Here we got the vertex data, and can see that I'm checking for encoding and non-encoding, and that's the same. Another array type, another type, and this is actually for the integers, for the indexes in the polygons. And it happens to be, can we dump out one of those files? I can run it from here. So I'm parsing through the FBX files, and when I found one of those TLV records, I write out what I know about them. So I found the name, the header extension, the creation type, creator properties. You can skip all those properties. A lot of properties, skipping those, skipping, a lot of them. Some places should be vertexes. And we got Here we got vertices, and some says we should have faces, or if it's called polygons, poly. There we go. So here we got a polygon vertex index, and we can find that in the binary dump if we look at it. And here I uncompressed the data, or it was uncompressed already maybe. And it says 0, 1, minus 3, 3, 4, minus 3, minus 6, 6, 7, minus 3. Yeah, and I just noticed that the file here started, the viewer started there, but so this file polygon vertex day index, vertex index here, apparently has a lot of minuses in the offset into the other arrays, and that was quite easy to calculate that a polygon ends with a negative number. So on the last number in the polygon, in the going to be the highest bit that can be set. So we got the vertex 0, 1, and 3 is going to be used for the polygon, and I write out poly here when I detect the polygon. So that's what this is doing. It's checking only use polygon, only use for polygon parsing, signed int. And this is test code, right? So I encoded in that this type is just for reading polygons. It could be much else in the file, but yeah, hard coding while testing out shit. And here she reads the record, and if it's a vertex, if it's a polygon vertex index, if a UV texture, UV index, it's a normal, so it has two. It not just has a polygon index into the vertex array, it also has a texture index into the texture array, which is really messed up. And I got normals. And here we got that it detects the different property types and reads it up with a different method for reading the different values. And that's just some more debugging. Reading a header, reading the header node, parse FBX. This is the method called to parse the FBX. And down here comes code for viewing it and a lot of test data. Yeah, I'm not totally sure I should upload this mess. I guess I will upload this mess with a big exclamation mark of this is a mess, expect it is a mess, use the as import library, start with reading the text wavefront files. Wasn't it called object? It was, but it's not. Yeah. Start with reading in those. You can do that, I'm sure. And after that, I would suggest you start with a 3DS format because it's so much easier. This is kind of easy. Try that one, you will be happy about that. If you go into Blender, you go into Blender, Preferences, you go into Add-ons, you search for 3DS, Import, Export, 3DS format, File, Export, 3DS. Now you can export to your binary 3DS, or of course you can export to FBX and you can export to wavefront. So you have all three formats there. And this is a long video, but for you that has stayed all this time, let's actually try to load a new object for real. Let's do that. And we're going to use mesh. So we need a mesh, right? And this is AI. So we're going to use mushroom man T-pose in realistic style, which isn't realistic. Then we click generate. When you sign up for Meshy, you get a few credits. I have 150 left. I created, I don't know, 10 or 15 or different objects. So this is an example of an object, as my face is of course in the way. And you see what the AI has created, and you know AI can create images. And I think this tool, the Meshy AI, Meshy.ai, just asks for 2 images, one from the front and one from the side, and then it calculates vertices from that. I think that's how it works. So here we have our mushroom man. Let's refine him. Then after we have refined him, we can download Meshy mushroom man. And I will cut out this because it takes a few minutes to generate. So yes, I will cut this out. So there we go. We have our final mushroom man. He looks a bit scary almost. He looks very mushroomy, which is the point though. I see an error in this, and this I noticed this a bit a lot with the AI. You see the legs are fused together. And well, the texture looks fine on top. Normally you get like odd textures on the top. So we're going to download this, and we can select, we actually can select our object files. If we want to read it in an easy text format, then select that and download that. And we can select the FBX, and I have an FBX loader, so I'm going to select FBX. It cost me 20 credits. Oh, okay. Let's download that. Let's click there. Mushroom Man. Let's extract the mushroom man. There we go. We got the texture and we got the model. Let's load in the model in Blender. So we're going to import FBX from downloads, mushroom man. Oh, there, mushroom man. So there we go. We need to re-export this because my loader, I know what to do. I know how to fix this, but I got a bug in my loader. Or not the bug, it's actually not the bug, it's just I haven't coded it. I don't call what I haven't coded for bug. I know what's wrong and I know how to fix it, so I won't call it the bug. It's an issue. It's a feature that's not implemented yet. So we go to mushroom man, polygons, and we going to go to transform geometry. Getting tired of English. Triangulate faces, because Meshy produces polygons with more vertices than 3. So some polygons has 4 vertices. My loader does not support that. I know exactly how to support it, I just hasn't. I actually have, but other story other day. My code is hack. It's hack, okay? So I'm just going to export that. So we got Mushroom Man exported, but now we need to load in the textures, and I should have written the texture loader, and I should use a PNG lib to read in this PNG, or I should convert it to Targa. Targa is an old format that's very simple to read, and I have a reader for that. But since I don't want to do that now, I'm just going to load this in GIMP, convert it, downscale it, convert it to a C file and include it, because I'm not there yet in my reader. So we're going to take this image, we're going to scale it to 256 times 256, and we're going to export it, and we're going to export it to where I exported the mushroom man. Mushroom man, there we go, the mushroom man, see mushroom man texture 256 times 256 times C, and I want to have name image data. This is struct. I need to name the struct. I'm not going to use glib types. I'm going to export that. Now we can open up my code. And the first we're going to do is include the texture. Include mushroom non-texture 256 256.c, and then we go down to where I load the file, and then we're going to load mushroom man. And the texture is totally whacked. That's not how it should look like. How did it look like here? Yeah, it's blue. Yeah, this texture doesn't really look like they should. That wasn't a great example. I will actually leave it like that. It works on some objects, apparently not this, and this makes the point that this code isn't finished. So maybe not download this code until I manage to finish it, and it does not have animations anyhow. But you got a lot of understanding of textual 3D objects. You got understanding of how the files work. You have got an understanding of how most binary files are structured, and with most I mean just a few, but enough many that it's actually quite useful to know the TLV structure of it. You know that the 3DS version, the older popular version, was using the TLV, and that's kind of easy to start with if you want to code a loader. And you got a bit of a introduction with totally shit code for an FBX viewer. So happy enjoy and happy coding out there. Okay, before we end this over an hour long thing, I actually scaled the image wrong when I did it. I scaled it to 254. 254 should be 256, 256. And when I rescaled the image, it came out fine. So here is the object in my viewer, and that's the object, the AI object from Meshi. So there you go. The viewer do work for object that is exported with polygons with 3 vertices, don't forget that, and the scaling down the texture or loading it with some library. And like I said, don't use my viewer here. It's not done yet, but I will keep working on it, so see you around.